Okay, in our case study today, we're going to be going over vigabatrin and how it treats seizures. And we're going to talk a little bit about the neurotransmitter GABA and how having a lower amount than normal of that can cause seizures and why we're taking this medication to help treat that. So we're going to talk about in this case study how GABA works as an inhibitory neurotransmitter, specifically the enzymatic inhibition mechanism of vigabatrin, and how that's going to be helping us there, how the knockdown of GABA vigabatrin will lead to the prevention of seizures, and the bound structure as well. All right, so how is GABA working as an inhibitory neurotransmitter? So we have inhibitory, we have excitatory neurotransmitter. So what we're talking about here is an inhibitory neurotransmitter. Neurotransmitters are chemical messengers. GABA is considered inhibitory because it blocks or inhibits brain signals and decreases activity of the nervous system. So it creates this calming effect. So we're going to see how that sort of helps avoid us from having seizures sort of by having that calming effect. So GABA attaches to a protein in the brain called the GABA receptor, produces that calming effect. So that helps people with reducing anxiety, stress, fear, and then preventing seizures as well. GABA decreases the neuron's action potential. So when the action potential drops below a certain level, so that threshold potential that it needs to be at, the neuron will not generate action potentials and not excite nearby neurons anymore, right? So the action potential is triggered. So when it drops below that certain level, that threshold, then the neurons aren't going to generate action potentials anymore. So they're no longer being excited. So when they get overexcited, that's when we're starting to see seizures happen. So how GABA is working as an inhibitory neurotransmitter, sort of going a little bit deeper into that, GABA activates chloride channels, and chloride, as we know, has that negative charge to it. So the charge outside of the neuron is more negative than it is on the inside. So then chloride channels open and it equalizes that difference. So there's a positive outward movement of a current so that the current inside of the neuron becomes more negative. Then the neuron communicates by becoming more positive. And then GABA decreases that current and inhibits neurotransmission in the adult brain. All right, so that's sort of step by step. So we're seeing the action potential here, and then sort of on this small graph, we see sort of how the threshold and the resting potential differ. And GABA is an inhibitory neurotransmitter that triggers opening of chloride channels in the postsynaptic neuron, which hyperpolarizes the membrane. So now vigabatrin, what are we doing with that? What exactly is it doing? What's the mechanism of action that we're seeing there? So it is an analog of GABA, which is used in the treatment of refractory seizures and infantile spasms. So what's happening here is there is an irreversible inhibitor of GABA transminase. So GABA T is the enzyme that's responsible for degradation of GABA. Okay, so what this medication is doing then is it's inhibiting that enzyme from breaking down GABA, which results in an increase of the amount of GABA in the cell, in the neurons, and then the concentration as a whole in our central nervous system. So what happens is we have glutamate, so that's sort of that precursor of GABA, and then there's GABA in the cells as well. So then what happens is they are sort of recycled out. So GABA gets recycled out once it does its job by inhibiting the action potential. It gets recycled out by GABA T. So what vigabatrin is doing is stopping that enzyme from tossing out the GABA. So now how is it preventing seizures? So kind of tying that all together, so what are seizures? A little bit about that. Seizures are characterized by excessive neural activity. So there's groups of neurons and they're all firing at the same time. So inhibitory neurons like GABA, they pump the brakes on all of those excitatory pulses. So what we're looking at here is we're seeing sort of the positive input of sodium, the positive input of calcium, and what happens here is what GABA does is opens up a chloride channel so that there's positive inside here, but now there's negative inside as well. So it sort of puts a balance in between the neurons. So then what you're going to see is that you're going to get that balance, and then when GABA is done being used, it's going to get recycled, right? So the action potential occurs when there's sort of this this balancing of the two when these channels are being opened. So when there's not enough GABA, that can cause neurons to become hyperexcitable. So that leads to seizures. So what we're seeing here is the neurons are becoming excitable. So when things are opening, they're all rushing in, but GABA sort of makes that stop. So it opens up this additional channel that stops that excitability from happening. So when that doesn't happen, we're just going to be having excited neurons, and they're just all going to be firing at once. It becomes really overwhelming, causing that seizure to occur. So since GABA is taken up by GABA T, by using vigabatrin, GABA T is inhibiting that GABA from being thrown out, so then it remains in the cells longer and inhibits that overexcitement of neurons. All right, so then the structure, this is sort of a 2D structure, but I have here as well a structure from Chimera that I have pulled up here so you can see sort of what vigabatrin looks like on the 3D scale. And here are citations, and that is the end of my case study presentation.